Now let us begin off with few concepts related to the topic of dynamics. Okay, so my first concept would be that of Newton's second law of motion, because that actually has some implication in the problem. So it is very basic law actually, so I need not go into much depth of it. I'll begin off with Newton's second law, which is basically the force is equal to the rate of change of momentum, okay, of a body, and if the mass of the body is constant, then the force is going to be given by m into dv by dt, which can be written as m into a, where a is the instantaneous acceleration of the body. Okay, fine. Newton's third law of motion: if I have got two bodies, this is my first body, this is my second body, body 2 applies a force F12 on body 1, and body 1 applies force F21 on body 2, then these two forces are basically going to be the action reaction pairs, and in the vector form it would be written as F12 equals minus F21 vector, okay, or F12 vector plus F21 vector is going to be equal to 0. Okay, so basically these action reaction forces are of the same magnitude, that is mod of F12 vector equals mod of F21 vector. Okay, they are of the same magnitude but their direction is opposite, which is simply indicated by this negative sign. Fine. Okay, now we move on to the next topic, that is friction. So basically we have two types of friction, one is static friction, the other one is kinetic friction. So static friction, okay, basically the only purpose of the frictional force is to reduce the relative motion between the two bodies, or to negate the tendency of two bodies to have any relative motion between them, provided they have some roughness in between them. If there isn't any roughness, or if there isn't any coefficient of friction between the two surfaces, then there won't be any friction actually. So there won't be any resisting force which would try to reduce the tendency of relative motion. But if there exists some coefficient of friction, then that frictional force is going to reduce the tendency of relative motion between the two surfaces. Static friction is also that type of force. Okay, static friction is basically a self-adjusting force. It is self-adjusting frictional force. Okay, static frictional force is self-adjusting frictional force. It acts between the two bodies only when there is no relative motion between the two bodies. Acts when there is no relative motion between the two surfaces, contact surfaces. Okay, okay, so it is basically a self-adjusting frictional force. Fine. And it attains its maximum value when there is a relative motion which is about to begin. Okay, so it attains its maximum value, which is equal to mu s into n, where mu s is the coefficient of static friction between the two surfaces and n is the normal reaction between the two surfaces. Fine. So it attains its maximum value mu s into n when the relative motion is just about to begin. Okay, fine. Okay, now let us move on to the next type of friction, which is kinetic frictional force. Okay, so this is my kinetic frictional force. It is not a self-adjusting frictional force. It has a constant magnitude, which is given by mu k into n. Okay, where mu k is the coefficient of kinetic friction between the two contact surfaces, and it is of constant magnitude. Okay, and it acts when the relative motion between the two surfaces have begun. Okay, fine. It should be noted that the static frictional force acts when there is no relative motion between the two bodies. It does not imply that the bodies do not move. There can be cases when the bodies actually move, but the only condition for the static frictional force to act between two bodies is that they do not have any relative motion. Let's say these two bodies move with the same velocity, okay, and the same acceleration. Let's say there is no relative motion between two bodies. These two bodies are moving, okay, but there is no relative motion on this surface. So in this case, the static frictional force is going to act between the two surfaces. Fine. Now let us talk about ideal strings. Ideal string an ideal string is massless and it is inextensible. Okay, and we also have something called ideal pulley. It is massless and it is frictionless. It is massless and frictionless. Okay, if in case of ideal string we have some tension developed, so that tension is going to be the same throughout. This is also another point which needs to be noted. Let's say I have this system, the tension is going to be the same throughout this whole string. Okay, so if tension T acts here, the tension T acts here also. Okay, fine. Let us now talk about constraint equations. Okay, so basically we would be dealing with two types of constraint equations. One would be string constraint equation, which is based on the fact that an ideal string is inextensible. This constraint equation applies only to ideal strings. Okay, so let's say, let me write down few things first. It is based on the fact that an ideal string is inextensible. Okay, so let's say I have a pulley, okay, and a single loop, a single string, a string basically loops over the pulley, and two masses are attached to the two ends of the string. Okay, so if let's say this mass is moving upwards with an acceleration of a1 and this mass is moving downwards with an acceleration of a2, we will divide this whole string into two segments. This would be my first segment, this would be my second segment. Okay, if I talk about this point is attached to the pulley and the pulley is not moving, so this point has got no tendency to extend or to shorten. Okay, now if I talk about this point is shortening with an acceleration of a1. Okay, so this whole segment of the string has a tendency to shorten itself by an acceleration of a1, so I will write down minus a1 for this segment of the string. Okay, now let me talk about this segment of the string. Okay, this point of the string is again attached to the pulley, fine, and the pulley is not moving, so this point has got no tendency to shorten or elongate itself, but this point is moving downwards with an acceleration of a2. Okay, fine, so this whole segment of the string has a tendency to extend itself with an acceleration of a2, therefore I'll write it plus a2. Okay, now this whole string, if taken all together, is neither extending nor shortening. Fine, so I will write down plus a2 minus a1 for this whole string. Okay, plus a2 for one segment of the string which is trying to elongate itself, and minus a1 for the other segment of the string which is trying to shorten itself. And since the total string as a whole is neither extending or shortening, I'll write this should be equal to 0, which gives me a constraint relationship between a2 and a1 as a1 equals a2. So this is how we obtain constraint relationship in simple cases. Now let us talk about another case. Okay, in this case the pulley would be moving. Let me draw the figure first. Okay, so this is my first pulley. This pulley is fixed with the wall, and I have a body which is attached to one end of the string, and I have another pulley which is attached to other end of the first string, and I have the second string which rolls over the second pulley, and I've got two masses attached at the two ends of the second string. Fine, so let's say this body is moving upwards with an acceleration of a3. Okay, this pulley is moving downwards with an acceleration of a4. Okay, and this body is moving with an acceleration of a2, and this body is moving with an acceleration of a1. Fine, now let us talk about the first string first. It has got two segments. I'll draw the first segment. Okay, this end is fixed, right? It is attached to the first pulley. So this end is fixed, this end is moving downward with an acceleration of a4. So while writing down the constraint equations, I'll write down the acceleration as plus a4 because it has a tendency to increase its length. This is my second segment. I'll draw it here. This end is attached to the first pulley. Fine. This end is moving upwards with an acceleration of a3. So this segment as a whole has a tendency to shorten with an acceleration of a3. Fine. So for the first string, I'll write down the constraint relation as a4 minus a3 plus a4 minus a3 must be equal to 0, which gives me the relationship between a4 and a3 as a4 equals a3. Fine. So this is my first constraint equation which I generate. Now let us talk about the second constraint equations which we can obtain from the second string. Okay, so this is my first segment of the second string. If I draw it here, this is my first segment of the second string. This end is attached to the second pulley. It is moving downwards with an acceleration of a4, and this end is moving downwards with an acceleration of a2. Okay, so I'll write down minus a4 because this end has a tendency to shorten the length of this segment of the string, plus a2. This is going to be for the first segment of the second string. Now let me draw the second segment of the second string. This is my second segment of the second string. Fine. This end is moving downwards with an acceleration of a1, and this end, since it is attached to the second pulley, it is moving downwards with an acceleration of a4. Fine. Okay, so I'll write down plus a1 because this end has a tendency to increase the length of the string, minus a4 because this end has a tendency to decrease the length of the string. Now if I write down the constraint relationship for the whole second string, I'll write down minus a4 plus a2 plus a1 minus a4 equal to 0, which gives me the constraint relationship as a2 plus a1 minus 2a4 equals 0. Now I can replace a4 by a3. So my constraint relationship becomes a2 plus a1 minus 2a3 equals 0. Fine. Now this is my simple constraint relationship. Fine. Now during the problems, I'd be able to relate the different accelerations via the constraint relations, and the problems can be solved by relating the tensional forces with the accelerations, and these accelerations then would have to be written in terms of tension. We'll get the tension from there, and from the tensions we would be able to find out the accelerations. Fine. Now let us talk about the wedge constraints. Fine. Now the wedge constraint is based on the simple fact that along the direction perpendicular to the contact surfaces, let's say this is my wedge, okay, and let's say this is my angle alpha, and I have a body here. This wedge is not fixed, it is moving, let's say, with an acceleration of a1 in the rightward direction, okay, and I have got this body. It has got two accelerations. I mean, its acceleration can be split into two components, let's say a2 and let's say this is a3. Okay, so this is basically my contact surface, and the wedge constraint is based on the simple fact that along the direction perpendicular to the contact surfaces, the two bodies are going to have the same acceleration. Along the direction perpendicular to the contact surface, let's say this is my contact surface, my first body, let's say this is my first body and this wedge is my second body. The first body has got an acceleration of a3, okay, and along the same direction my wedge has got an acceleration of a1 into this angle is nothing else but 90 degree minus alpha. Fine. So this component is nothing else but a1 into sine of alpha, that is a1 into cos of 90 degree minus alpha. Basically this angle is 90 degree minus alpha. Fine. So according to the wedge constraint, a3 must be equal to a1 into sine of alpha. Fine. So this is my simple wedge constraint. Fine. Now let us begin off with few problems in the topic of dynamics. The first problem is this. Okay. In the arrangement of figure given, the masses m0, m1 and m2 of bodies are equal. The masses of the pulley and the threads are negligible and there is no friction in the pulley. Find the acceleration W with which the body m0 comes down. Also find the tension of the string or the thread binding together the bodies m1 and m2. Okay, so in this problem I have got this setup. Okay, this is my setup. The pulley is frictionless, there is no friction between the body and the floor. Okay, fine. So this is the setup which has been given to me and I have been asked to find out the acceleration W with which the body m0 comes down. So let's say W is the acceleration with which the body is coming down. The body of mass m0 is coming down. Fine. And I also need to find out the tension. Let's say tension T2, which is binding together the bodies m1 and m2. Okay, so these are the two things which I need to find out. Fine. Now the thread is ideal. Fine. The thread is ideal, which implies that it is not extensible, which implies that if the body of mass m0 is moving downwards with an acceleration of W, these two bodies m1 and m2 are also going to move with the acceleration of the same magnitude, since the threads are inextensible. Fine. So I'll say that m1 and m2 also move with the same acceleration in the leftward direction. Okay, fine. Okay, now let's say that in this segment of the thread the tension is T1, so it would be T1 in the upward direction for mass m0 and T1 would be in the leftward direction for mass m1. Okay, fine. Now these two masses, that is m1 and m2, they are moving with the same acceleration, that is the magnitude of the acceleration as well as the direction of the acceleration is same for both mass m1 and m2, which implies that mass m1 and m2 can be combined as a single body. So I'd say that mass m1 and m2 can be combined as a single body and all the internal forces which are acting between those two bodies can be neglected. So in this case the internal forces which is acting between mass m1 and m2 is T2, so that can be neglected. Okay, if I combine the two bodies, fine, so the only external force which is acting on the combined mass m1 and m2 is T1 in the leftward direction. Of course there is going to be a weight acting downwards, that is m1 plus m2 into g, which is going to be balanced by the normal reaction which would be provided by the floor. Okay, fine. So along the y direction the forces are going to be balanced. I am not much concerned about the y direction because there in that direction the forces are of course going to be balanced. This combined mass is going to move with the same acceleration as that of individual masses m1 and m2. So if I write down the force equation for this FBT along the x-axis, I'll write T1 equals m1 plus m2 into W. Okay, so let's say this is my equation 1. Okay, okay, now if I write down the force equations for body of mass m naught, first let me draw the FBD, the free body diagram for mass m naught. Okay, so for mass m naught, there is its weight acting downwards, which is m naught into g, and there is tension force which is acting upwards, that is T1. Okay, fine. So this body is also moving downwards with an acceleration of W. So if I write down the force equation, I'll write m naught into g minus T1, because T1 is acting in the upward direction, must be equal to m naught into W. So let's say this is my equation 2. Fine. So from this particular expression, I can replace T1 in this expression. Okay, so this gives me m naught into g minus m1 plus m2 into W equals m naught into W, which on solving will give me the acceleration with which the mass m naught moved downwards as m naught g upon m1 plus m2 plus m naught. So this is going to be the acceleration with which the body of mass m naught is going to move in the downward direction. Okay, now let us move on to the next subpart of this problem, which is in which I have to find out the tension which is acting between the two bodies m1 and m2, which basically holds the two bodies together. Okay, so basically that means I need to find out T2. Okay, now this body m2 is moving in the leftward direction with an acceleration of W. Okay, so if I draw the FBD of body m2, the external force is acting on it is T2 in the leftward direction, its own weight acting downwards, and which is being balanced by a normal force, let's say N1, which is being provided by the ground, and it is acting in the vertically upward direction. Okay, fine. So this m2 is moving in the leftward direction with an acceleration of W. So if I write down the force equation along the x-axis, that is the horizontal axis, I'll write T2 equals m2 into W, and I know the value of W from this expression. So if I replace W in this particular expression, I'll get T2 as m2 into m naught g upon m1 plus m2 plus m naught. Okay, so this is going to be the expression for the tension which is acting between the two bodies m1 and m2, which is actually holding them together. Fine. Let us now move on to the next problem in the topic of dynamics, which is this. Okay, find the acceleration of rod A and wedge B in the arrangement shown in the figure below. If the ratio of mass of the wedge to that of the rod equals eta and the friction between all contact surfaces is negligible. Fine, so this is basically my diagram. Okay, and this is my rod and this is my wedge. Fine. Okay, now the ratio of the masses of wedge to that of rod is given to me as eta. So I'll say that eta is equal to mass of wedge upon mass of rod. Okay, so this is my figure. Now I need to note down few things in this figure. The rod is positioned such that it is fixed to move only vertically. Okay, basically these two things bar the rod to move only in the vertical direction. Fine, so the bar is always going to move vertically. The wedge is on a horizontal surface which is frictionless, so the wedge is going to move only horizontally. Fine. Okay, so this is my situation of the problem, and I need to find out the acceleration of the wedge and that of the bar. Okay, fine. Now let us now draw the free body diagrams of the wedge and the bar. Okay, so let me draw the bar first. So this is my bar. Okay, this angle is going to be nothing else but alpha. Fine. Now it has got a weight acting downwards, mr. Okay, and there is going to be a contact force between the bar and the wedge, and on the wedge the contact force is going to be directed in this direction. Let's say its value is m. Fine. Okay, now let's say that this rod or bar has an acceleration a r in the vertically downward direction. Okay, fine. Now let me draw the FBT of the wedge. Fine. So this is my wedge, this is my angle alpha, and there is going to be a weight acting downwards, mw into g. Okay, and there is going to be a normal force acting between the rod and the wedge, and on the wedge the normal force would be directed in this direction. Its magnitude is going to be same as that of this value, and these two forces are going to be balanced in the vertical direction by the normal force which would be provided by the ground. Let's say it is ng. Fine. Okay, now this wedge is going to move only in the horizontal direction. Let's say it is moving in the horizontal direction, definitely is going to move in the rightward direction. Fine. So let's say that the magnitude of the acceleration of the wedge towards the rightward direction is aw. Fine. Now I need to note few other things in this problem. The first being that the rod and the wedge, they are always in contact with each other. Okay, so if they are always in contact with each other, I'll get one equation which would be a constraint equation. Fine, which would give me the relationship between the acceleration of the rod and that of the wedge. Fine. Okay, now let me draw the accelerations of the wedge and that of rod along the direction which is perpendicular to the contact surface. Fine, along that particular direction the acceleration components are going to be same. Basically what I mean to say is that along this particular direction, let's say this is my contact surface, okay, of the rod and the wedge. So along this direction, that is the direction perpendicular to the contact surface, the acceleration of the component of the acceleration of the rod and that of the wedge is going to be the same. Fine. So this is my acceleration of the wedge. Its component along this direction is going to be aw into, it would be aw into sine of alpha. Okay, and this is my acceleration of the rod ar, and along this direction the component is going to be equal to ar cos alpha. Okay, so along this particular direction, that is the direction perpendicular to the contact surface, the component of the accelerations is going to be same, which gives me the first equation, which is the constant equation, as aw sine of alpha equals ar cos of alpha. Okay, so this is my first equation. Fine. Okay, now let us now figure out the other equations. Fine. Note that in the case of the rod, there are going to be horizontal forces applied by these two walls, which is going to ensure the horizontal equilibrium of the rod. Okay, so I haven't mentioned that basically since the rod is moving in the vertical direction with some acceleration, so there is going to be some vertical inequilibrium in the rod. Along the horizontal direction, the rod is going to be in equilibrium. Fine. So now let me write down the force equation for the rod along the vertical direction. So I'll write down mrg g minus n cos of alpha, which is the vertical component of this contact force. This must be equal to mr into ar. Okay, this whole equation has been written considering downward as my positive direction. Okay, this is my second equation. Okay, and let me write down the third equation then, which would come out from this FBT of the wedge. Okay, so my third equation becomes n sine of alpha equals mw into aw. Okay, this whole equation has been written considering horizontally rightward as my positive direction. So this is my third equation. Okay, so in this problem I have got three equations. Okay, and I've got four unknowns. Actually my fourth equation is this. So I've effectively got four equations and four unknowns. This has been given to me in the problem. Fine. So I can basically replace mw by mr as eta in my answer. Okay, so I've got four equations, four unknowns. I can get my values of ar and aw. Okay, so fine. So on solving, I'll get the acceleration of the rod, which is vertically downwards, as ar is going to be equal to g into 1 plus eta into cot square alpha inverse. Fine. I haven't solved these equations. Okay, I expect you to solve these equations. I'm just writing down the answers. Fine, because I expect you to know to solve these equations. Fine. So this is my vertical acceleration of the rod, and my acceleration of the wedge is going to be equal to aw into tan of alpha, which is going to be g tan of alpha into 1 plus eta cot square alpha inverse. Fine. So this is going to be my acceleration of the wedge in the horizontal direction. Fine. The problem was pretty simple. I basically needed to find out the constraint equation, which was basically important in this equation, in this problem. Okay. Let us now move on to the next problem in the topic of dynamics, which is this. In the arrangement in the figure, the masses of the wedge capital M and the body small m are known. The appreciable friction exists only between the wedge and the body M, the friction coefficient being equal to K. The masses of the pulley and the thread are negligible. Find the acceleration of the body M relative to the horizontal surface on which the wedge slides. Okay, so this is basically the diagram which has been given to me. There is a wedge which is moving in a frictionless surface. There exists a friction between the wedge and the small block of mass M. Fine. Now this end of the string is fixed. Okay, and there exists some appreciable friction, the friction coefficient being equal to k. Okay, fine. So I need to find out the acceleration of the body m relative to the horizontal surface on which the wedge slides. Okay, so let me first draw the FBDs, the free body diagrams of the wedge and the small block of mass m. Okay, so the FBD for the wedge is going to be something like this. This is my wedge. Okay, since the block is going to move downwards, the wedge is going to move rightwards. There is going to be some normal force acting between the wedge and the block. The normal force on the wedge is going to be directed in the leftward direction. Let's say its magnitude is equal to n1. Okay, and since the block is moving downwards, the relative motion of the block with respect to the wedge is in the downward direction. So the frictional force which the block is going to apply on the wedge is also going to be in the downward direction. Its magnitude is going to be equal to k into n1. Okay, there is going to be a weight mg acting downwards. Okay, and there is going to be a tension force which this particular segment of this string is going to apply on the wedge via this small rod which attaches this wedge to the pulley. Okay, fine. So let's say its magnitude is d. Okay, and there is going to be a normal force which is going to be provided by the ground, which balances all the forces in the vertical direction. Okay, so let's say its magnitude is ng. Okay, now let us draw the FBD of the bar. So this is my bar. It is going to have its own weight acting downwards, mg. It is moving downwards. The wedge is going to apply a frictional force k into n1 in the vertically upward direction, and there is going to be a horizontal force, that is the contact force between the wedge and the block. Okay, its magnitude being same as that of this. Okay, basically these two are action reaction pairs. Okay, and there is going to be a tension force which this string is going to apply on the block. Okay, its magnitude is going to be the same as that of any other point in the string. Okay, so this is my FBD of this block. Let's say this block is moving downwards with an acceleration of a1. Okay, and this wedge moves in the rightward direction with an acceleration of a2. Okay, fine. Since the wedge and the block, they are in contact with each other along the horizontal direction, the block has to move with an acceleration of a2. Okay, so I have been asked to find out the acceleration of the body m relative to the horizontal surface on which the wedge slides. Basically, I need to find out the acceleration of the body m with respect to an inertial frame of reference. So the net acceleration is going to be root over a1 square plus a2 square. Okay, now there is going to be a constraint equation which is going to be obtained by using the fact that this thread is inextensible. Fine. So this thread has got three segments. The first segment being this segment, because the block is moving downwards with an acceleration of a1, it has a tendency to stretch itself with an acceleration of a1. Okay, so this segment has a tendency to stretch itself with an acceleration of a1. This segment is not having any change in its length, fine. So there isn't any tendency of this segment to stretch or to compress, fine. This segment of the string is having an acceleration. Basically this end of this segment of the string is shortening with an acceleration of a2. Okay, fine. So this segment has a tendency to shorten, fine. So if I write down the constraint equation, I'll write plus a1 because this segment has a tendency to stretch with an acceleration of a1. So if a segment has a tendency to stretch with an acceleration of a1, I'll write positive. This segment has a tendency to shorten with an acceleration of a2, so I'll write minus a2. This must be equal to 0 since the total length of the string is neither stretching nor shortening. Okay, so I get my relationship between a1 and a2 as a1 equals a2. Okay, so from where I can write a net as root 2 a1. Okay, so I basically now need to find out the value of a1. Okay, fine. Now let us obtain the force equations from the FBD of the wedge. Along the vertical direction there is going to be vertical equilibrium. Along the horizontal direction it is moving with an acceleration of a2. So if I write down the force equation along the horizontal direction, I'll write T minus N1 equals capital M into a2, which can be written as a1. Okay, from this expression. So I'll write this. So this is, let's say, my first equation. Okay, fine. Now let us obtain few other force equations from the FBD of the block. Okay, so along the vertical direction, if I write down the force equation, I'll write down mg minus kn1, which is the frictional force acting in the vertically upward direction. Okay, fine. Minus T, which is the tension force, must be equal to ma1. So this is my equation 2. This whole equation has been written keeping vertically downwards as positive, and this equation, the first equation, was written keeping horizontally rightward as positive. Fine. Okay, now if I write down the force equation along the horizontal direction for this bar, I'll write down N1 must be equal to small m into a2. So this is my third equation. Sorry, this can be written as a1. Fine, because a1 equals a2. Fine. So in this problem, now I have got 3 unknowns, 3 equations. I can easily obtain the value of a1. Okay, so I'm again not solving the equations, I am straight away writing down the value of a1. So a1 turns out to be mg upon m into 2 plus k plus m. Okay, and the net acceleration therefore turns out to be root 2 a1. So it can be written as root 2 into mg upon m into 2 plus k plus capital M. Fine. So this is going to be the acceleration of the block with respect to the surface, that is the ground on which the wedge is moving. Fine. Now let us move on to the next problem, which is this. A small body A starts sliding off the top of a smooth sphere of radius capital R. Find the angle theta corresponding to the point at which the body breaks off the surface of the sphere, as well as the breaking of velocity of the body. Fine. So in this problem I have a small body which is on the top of a smooth sphere initially. So this is my sphere. Okay, it has got radius R, capital R, and my body was initially at the top of the sphere. It started sliding off with zero initial velocity from the top, and eventually it left the contact with the sphere, let's say at an angle of theta and with a velocity of v. I basically need to find out the angle at which the body breaks off with the sphere. So basically I need to find out theta and the velocity with which the body breaks off from the sphere. Okay, fine. So when the body is about to break off from the sphere, there is going to be no contact force acting between the body and the sphere. Fine. So the centripetal acceleration which the body requires in order to move in this path is going to be just provided by the component of its weight along the radially inward direction. What I mean to say is that if the body left contact, the centrifugal force, that is mv v square by r, is going to be balanced by the component of the weight, that is mg, acting along the radially inward direction, which is mg cos of theta. Basically this mg cos of theta is going to be the centripetal force acting in the reference frame of the ball, which is of the body, which is a non-inertial frame of reference. I have to apply a centrifugal force. Okay, had I been solving in inertial frame of reference, I would have dealt in terms of centripetal forces only. Okay, so the forces are going to be balanced in this direction. Okay, so I'll write down mv square by r must be equal to mg cos of theta. This is going to be my first equation. Fine. Now this sphere is smooth, which implies that there is no dissipation of energy, dissipation of the total mechanical energy as the body falls down. Fine. So finally the body has some kinetic energy. If I say that this is my reference level, finally the body does not have any potential energy. Initially the body did have some potential energy. The potential energy was due to this elevation. Okay, so the potential energy which the body initially had would be given by mg into this height. This height is going to be nothing else but r into 1 minus cos of theta. It can easily be derived. Okay, that's not much of an issue. So mg into r into 1 minus cos of theta, this is going to be my potential energy, initial potential energy stored in the body. This must finally get converted into the kinetic energy of the body, which is half mv square. Okay, fine. So from here I get mv square by r as 2r, mv square by r as 2g into 1 minus cos of theta. Okay, fine. Basically this was my second equation. So if I replace mv square by r in this expression, I'll write 2g into 1 minus cos of theta equals sorry, there must be M. Okay, basically I have got R from this point to this point, okay, in the denominator of RHS. So mv square by R turns out to be, let me write it down more properly, mv square by R turns out to be 2 mg into 1 minus cos of theta, okay, and that is what I substitute here, okay. So I'll write down 2 mg into 1 minus cos of theta equals mg cos of theta, okay. I get mg cancelled from both the sides, which gives me 2 equals 3 cos of theta, which gives me theta as cos inverse 2 by 3, which is nearly equal to 48 degrees, okay. So this is going to be the angle at which the body is going to break off from the surface of the sphere. I needed to find out the velocity of the body as it loses its contact. So v square is going to be nothing else but, if I cancel m from both the sides, v square is going to be nothing else but 2 rg into 1 minus cos of theta, that is 1 minus 2 by 3. So it turns out to be 2 rg by 3, which gives me v as root 2 rg by 3, okay. So this is going to be the velocity with which the body is going to lose contact with the sphere. Fine. Now let us move on to the next problem in the topic of dynamics, which is this. A device consists of a smooth L-shaped rod located in a horizontal plane and a sleeve A of mass m attached by a weightless spring to a point B. The spring stiffness is equal to K. The whole system rotates with a constant angular velocity of omega about a vertical axis passing through a point O. Find the ratio of the elongation of the spring to the original length of the spring. Fine. So in this problem I have a device which consists of an L-shaped rod. Let me now draw an L-shaped rod. This is my L-shaped rod, okay. Fine. Okay, so this rod is actually mounted on a stand, okay. This is my point B, okay, and I have a spring which is fixed at point B, okay, and the other end of the spring consists of a body of mass m, okay. Fine. The stiffness constant of the spring is equal to K, and this whole rod rotates with an angular velocity of omega, okay. This is my vertical axis and it rotates about this vertical axis. So I need to find out the ratio of the elongation of the spring to the original length of the spring. So in an undeformed state, let's say the spring had length x. Since this rod has begun to move with an angular velocity of omega, there is going to be some extension in this spring, okay. Fine. Now if I look at the top view of this rod, it is going to be something like this. This is going to be my rod, okay. this is going to be a mass. The spring would have extended by some length, let's say delta x, and initially it had length x. Okay, this whole body is moving in a circular path with an angular velocity of omega. Okay, so since it is moving with a circular path, it would require a centripetal force whose magnitude is going to be given by m into omega square into r, where r is the radius of the circular path. Okay, fine. Now I basically need to find out delta x upon x. Okay, fine. This centripetal force is going to be provided by two forces. This centripetal force is basically going to be a result of two forces, a resultant of two forces. One would be the normal force which this rod is going to provide on the body, and the other would be the spring force which the spring is going to apply on the body. The spring force is going to have a magnitude k into delta x. Let's say in equilibrium this angle is theta. Okay, fine. So if I write down the equilibrium equations for this body, I'll write down n must be equal to m omega square into r into cos of theta. Okay, fine. And my second equation would be m omega square into r must be equal to m omega square into r into sine of theta, that is this component of the centripetal force must be equal to k into delta x. Okay, fine. Now sine theta is going to be equal to x plus delta x upon r, isn't it? It is very much clear from this diagram. Basically it is a diagram of right angle triangle. This length is x plus delta x and this angle is theta. So sine theta is equal to x plus delta x upon r. If I replace sine theta here, I'll get m into omega square into r into x plus delta x upon r equal to k into delta x. Okay, r gets cancelled, so this gives me m omega square x as delta x into k minus m omega square. Okay, so this gives me delta x by x as 1 by k upon m omega square minus 1. Okay, so this is what I had to find out. I had to find out the ratio of the elongation of the spring to the original length of the spring. Fine. Now let us begin off with the next problem in the topic of dynamics, which is this. Two touching bars 1 and 2 are placed on an inclined plane forming an angle of alpha with the horizontal as given in the figure. The masses of the bars are equal to m1 and m2 and the coefficient of friction between the inclined plane and these bars are equal to k1 and k2 respectively, with k1 greater than k2. find the force of interaction of the bars in the process of motion, and in the second subpart of the question I need to find the minimum value of the angle alpha at which the bars start sliding down. Okay, so in this problem this is my setup. Okay, and I have been given an inclined plane which makes an angle of alpha with the horizontal, and there are two bars of masses m1 and m2. Okay, and the coefficient of friction between the bar of mass m1 and the inclined plane is k1, and that of the bar of mass m2 and the inclined plane is k2. I have been given the condition that k1 is greater than k2. I need to find out the force of interaction between the bars in the process of motion. Fine. Now let us assume that the incline was frictionless and the individual bars m1 and m2 were moving in the inclined plane. Fine. Now let us assume that the inclined plane did have some friction, okay, and the individual bars were moving on the inclined plane. Fine. Now let us consider first that bar 1 was moving in the inclined plane. Okay, so only bar 1 was moving in the inclined plane. Fine. So the coefficient of friction between bar 1 and the inclined plane is equal to k1. The acceleration with which the bar 1 is going to move in this direction, let's say, is a. Okay, so there is going to be some frictional force which is going to be directed in this particular direction. Its magnitude is going to be equal to k1 into m1 into g into cos of alpha, and there is going to be a force which would be acting in this direction due to the component of gravity, which would be m1 into g sine of alpha. Okay, fine. So the equation of motion in this particular direction for this bar of mass m1 would be given by m1 into g sine of alpha minus m1 g cos of alpha into k1 is equal to m1 into a. Okay, which gives me the magnitude of acceleration of mass m1, let's say, as g sine of alpha minus k1 into g cos of alpha. Fine. Now similar would be the result for if I consider this particular case for mass m2. Okay, the result would be, let's say in that particular case the body of mass m2 was moving down the incline with an acceleration of a2. The acceleration would be given by g sine of alpha minus k2 into g cos of alpha. Okay, now why I derived out these two expressions was just to compare the magnitude of these two accelerations if the bodies were individually moving in this rough inclined plane. Fine. Clearly from this expression, since I know that k1 is greater than k2, I can say that a2 is going to be greater than a1. Now this expression implies that the mass m2 has a tendency to move with greater acceleration on this rough inclined plane as compared to mass m1. In other words, mass m2, if moved individually, is going to move with a greater acceleration than mass m1 on this inclined plane. Okay, so if these two bodies are going to move together on this inclined plane, I can now say that the masses are definitely going to move together, which implies that there is always going to be some force of interaction between the bars during the process of motion. So basically I derived these two expressions just to prove that there is going to be some force of interaction in the process of motion. Okay, had the mass m1 moved with a greater velocity, a greater acceleration as compared to mass m2, then there wouldn't be any contact after the two bodies were released, right? So, but my expression turned out to be this, which implied that they are going to be in contact, which implies that there is going to be some force of interaction between the bars during the process of motion. Fine. So now let us now proceed with the problem. Okay. Now, if I say that between these two masses m1 and m2 there is going to be a force of attraction, let's say a force of interaction, let's say of magnitude f. Okay, so if I draw the FBD of mass m1 now, the force of interaction is going to be acting in this direction, okay, on mass m1, okay. Fine. And there is going to be a component of its weight acting down the incline, which is going to be nothing else but m1 into g into sine of alpha, and there is going to be a frictional force which is going to act up the incline because the two bodies are going to move downwards, and that frictional force is going to be given by k1 into m1 into g cos of alpha. Okay, fine. Similar would be the FBD for mass m2. Okay, its weight component is going to act down the incline, whose magnitude would be m2 into g sine of alpha. Okay, and there would be the force of interaction acting in this particular direction, that is up the incline, and there would be frictional force acting in this direction, whose magnitude would be k2 into m2 into g into cos of alpha. Okay, now these two bodies are in contact, which implies that they are going to move downwards with the same acceleration. Okay, so let's say the acceleration is a. Fine. Okay, now let us now write down the equation of force equations down the incline. Okay, so I'll write down for this particular setup, for this particular FBD, I'll write down my force equation as m1 into g into sine of alpha plus f minus k1 m1g cos of alpha equals m1 into a. Let's say this is my equation 1, which I got from my first FBD. Now let us write down the force equation for my second FBD. I'll write down m2g sine of alpha minus f minus k2 into m2g cos of alpha equals m2 into a. So let's say this is my equation 2. Okay, now if I divide the equation 1 by m1 and equation 2 by m2, and if I subtract these two equations, I'll get g. What I'm doing is that I'm dividing this expression by m1, this expression by m2, and I'm then subtracting the second equation from the first equation. Okay, so I'll get g into sine of alpha plus f upon m1 minus K1 G cos of alpha minus G sin of alpha minus F by M2 minus K2 G cos of alpha equal to 0. Okay, so I get this G sin alpha cancelled. Okay, and then I get an expression like F into 1 by M1 plus 1 by M2 equals K1 G cos of alpha minus K2 G cos of alpha. Okay, so from where I get my expression of F as K1 minus K2 into G cos of alpha into 1 by M1 plus 1 by M2 inverse. Okay, so this is going to be my force of interaction between the two bodies during the process of motion. Okay, now in the second subpart of the question, I had to find out the minimum value of the angle alpha at which the bars start sliding down. This simply implies that the net force on the bar of mass m1 in this particular case is going to be equal to 0. Okay, so that basically would mean that I'll have this thing as 0 in that case. Okay, fine. So my equation would turn out to be m1 g sin of alpha plus k1 minus k2, that is f. Okay, I'm simply replacing f here. Okay, into g cos of alpha into m1 into m2 by m1 plus m2 minus k1 m1g cos of alpha equal to 0. Okay, so this is my expression. Okay, so in this expression I get m1 cancelled throughout. Okay, also get g cancelled throughout. Fine, so my expression becomes sin of alpha plus k1 minus k2 into cos of alpha into m2 by m1 plus m2 minus k1 cos of alpha equal to 0. Okay, so this can again be written as sin of alpha plus k1 into cos of alpha into m2 minus m1 plus m2 by m1 plus m2 minus k2 m2 cos of alpha upon m1 plus m2 equal to 0. Okay, so I get m1 cancelled here. Okay, so this becomes sine of alpha plus sine of alpha equals k1 m1 plus k2 m2 into cos of alpha upon m1 plus m2. Okay, so that gives me tan of alpha as k1 m1 plus k2 m2 upon m1 plus m2. Okay, so this gives me the minimum angle required for the motion to begin as tan inverse of k1 m1 plus k2 m2 upon m1 plus m2. So this is basically my expression which I needed to find out. Okay, note that I considered the first expression because it would be the first body, I mean the body of mass m1, which would have lesser tendency to move as compared to body of mass m2. So if m1 starts moving, definitely m2 is going to start moving. So my critical condition becomes this, okay, and not this. Fine. So this is the answer for the first sub part, and this is my answer for the second sub part. Fine.